Let's return to those sine and cosine functions for a moment. I looked at the area between those two curves, but I capped it off at two different coordinates where the sine function and the cosine function cross each other. If I wanted more area than that, there's going to be some places where the cosine function is on top, and there's going to be other places where the sine function is on top. I can take that into account in my formula, but it requires me to do a little bit more work. So if I have two different functions which cross each other multiple times, I need to keep track of which function's on top in which different regions. So here is a picture of just some arbitrary graphs of functions. I don't know what they are at all. Maybe one of them is a sine function. Maybe one of them is a parabola. No formulas are given. But I can see from the picture, there are places where the curve f of x is on top, drawn here in pink, and there's places where the blue function, g of x, is on top. So altogether, this is defining three separate regions that we've labeled S1, S2, and S3. We can integrate each of those separately and add it all back together at the end. So if you really wanted to, calculate area for the region S1, for S2, for S3, and so on, my total amount of area is going to be the sums of all those different area integrals put back together at the very end. Now, the way we can write that formulaically is we're saying that sometimes the function f of x is on top, so those will be the places where I subtract and write f of x minus g of x. There will be some places where the function g of x is on top, and those will be the places where I write g of x minus f of x. I can bundle that up all very nicely and just look at the absolute value of f minus g. So in the places where f is on top, absolute value of f minus g is f minus g. In the places where g is on top, absolute value of f minus g is g minus f. So that makes my formula very nice to write. And now I don't even care about which function's on top. The area between the curves f of x and g of x, between coordinates x equals a and x equals b, is equal to the integral from a to b of the function absolute value of f of x minus g of x, all dx. So the formula is very nice to write, but when we actually go to calculate it, we still need to split and know which function's on top, which function's on bottom. Let's take a look at that. So let's look at those sine and cosine functions again, but now we're going to measure the area from x equals 0 up to x equals pi over 2, something like this. So I get two distinct regions. Between 0 and pi on 4, it's the cosine function which dominates, the cosine function which is larger. Between pi over 4 and pi over 2, it's the sine function which is larger. So what I need to do is set up separate integrals for each of those. So what that's going to look like, here's my formula. Integrate the absolute value of cosine of x minus sine of x, all dx, from 0 to pi over 2, and using the absolute values there. I'll break that down into two different area integrals. The one of them with the cosine function on the top. So I'm integrating cosine of x minus sine of x. That's between 0 and pi over 4. I got those coordinates from looking at the picture. The second area integral is the region where sine of x is on top. So I'm integrating sine of x minus cosine of x, again between pi over 4 and pi over 2. I got those coordinates from my picture. Now, each of these functions gives me a very nice antiderivative to work with. I use my fundamental theorem of calculus, and I'm left with I'm trying to talk too fast. I'm left with twice the square root of 2 minus 2. Now, one thing that's interesting, at least to me, is that both of the smaller area integrals gave me the same number separately. They both gave me 1 on root 2 plus 1 on root 2 minus 1. Or over here, it's been written as -1 plus 1 on root 2 plus 1 on root 2. I'm not surprised by that because in my picture, there's a symmetry in these graphs. So for this problem particularly, I see that the area in pink is actually equal to the area in blue. And that geometric observation is reflected in my calculation here. I do get the same number twice. That's kind of a cool thing.